Okay, so we're doing 4.1 because you can't do chapter 6 without it. We're planning on doing inverse functions for each of the sine, cosine, tan, secant, cosecant, cotangent graphs that we've done. So we plan on talking about inverses. We plan on talking about inverse graphs. We need to talk about all that. But if you don't know what an inverse function is, that would make it kind of tricky to do. So we're going to rewind back to a chapter 4 concept. Tomorrow's 6.1. Okay, so the first thing you need to know is what you already know. We need to review it. So let's go over some of these basics. So a relation is anything that looks like this, right? Y equals x. Y equals 2. Y equals x squared. X equals y squared. X squared plus y squared equals 4. These are all relations. Right? Relations. Okay, so some of these are functions, some of these are not functions. Okay? Let's do one more. Y equals sine x. Okay, so someone just give me any number for x. Just give me a number. 3. Okay, so if let's say we let x be 3, right? So if you let x be 3, the first one's going to give us y equals 3. The second one's still going to give us y equals 2. It doesn't matter what you plug into y equals 2. For x, if there's no x, then there's nowhere to plug it in. So if x is 3, or if x is a million, y is 2 on that second one. The third one, of course, would be y equals 9, right? The fourth one is going to be 3 equals y squared. And then the next one would be 9 plus y squared equals 4, see? And the next one would be y equals sine 3. So some of these are going to give us a single answer for y. Others might give us multiple answers for y. Okay, so let's look at the first one. We got exactly one value for y. That means that y equals x up there is not only a relation, but it's a function. Okay? The next one gave us y equals 2. That means y equals 2 is a function. The next one we got a single answer 9. So y equals x squared is a function. This next one isn't quite solved yet. You'd have to square root both sides, and you would get y equals plus or minus rad 3. So we would say that x equals y squared is not a function, right? The same thing happens on this next one. In fact, this doesn't give us any solutions at all. I should have probably picked maybe 49 for the right side. Let's switch that. Let's make that x squared plus y squared equals 49, since you guys picked 3. This is going to give me y equals plus or minus rad 40. Again, that's not one answer. And this next one's going to give me exactly one answer. Y equals sine 3. You can get that on your calculator. So I'm going to punch that in. I assume it means 3 radians. So let's just type sine 3. 0.1411. Y is approximately 0.1411. Okay, so most of these gave us one answer. It was just the x equals y squared and the x squared plus y squared equals 49 that gave us 2 answers. So of all the ones up above, they're all relations, but most of them are functions, and these 2 with x's are not functions. So let's just write as a reminder here that a function is a relation where there is exactly one y for each x, or I should say at most one y for each x. There is at most one y value for each x value. Okay, another way of saying that is a function is a relation whose graph passes the vertical line test. You could say it that way too. A function's graph must pass the vertical line test. I will refer to the vertical line test in this class as VLT. Okay, VLT. So I wonder what we would call a function that passes the horizontal line test. Let's talk about that for a minute. See, up above here we have 6 functions. Maybe even know what they look like. So this first one is just a line like that, right? The second one is just a line like that. This one is the parabola at the origin. This one you may or may not recognize, but it looks like this. Notice it's not a function. This one, I heard some of you say it, is a circle. The radius is actually 7. And sine x, we've just got done graphing those ad nauseum, so we have that graph memorized as well. So we actually know what all these graphs look like, except maybe you didn't know that fourth one. But what we notice is that they all pass the vertical line test except for the sideways parabola and the circle. But some of them also pass the horizontal line test, which this class has never talked about before. So if you look at the first graph, right, you can draw horizontal lines on the thing, and it also contacts it at most once. Same thing happens on the third one. If you, I'm sorry, this one. Wait.
No.
Actually, it's the only other one. Yeah. Of all the functions.
X equals y squared.
Yeah, but it's not a function. Of all the functions that are on here, that's this first, second, third, and sixth one, only the first one passes the horizontal line test. See that? Yeah. Like if you draw horizontal lines, you're going to get one contact point on that first graph. Okay? All right. So we would call this first one here 1-to-1. This guy here in green. He's very special. He's 1-to-1. So let's write a new definition. A 1-to-1 function is a relation where there is at most one y value for each x value and one x value for each y value. That's new for most of you. Maybe you heard your teachers say 1-to-1 last year, but it wasn't a huge emphasis, just a little bit when you're talking about inverses and things. So you have to be really careful when you're drawing a 1-to-1 function. Here's why. Let's say you're drawing a function, I say, everybody draw me a 1-to-1 function, that'd make a great problem on my test. Just everybody draw a 1-to-1 function. You would need to draw it where it's always rising or always falling. Okay? Now, it cannot have any relative extrema. Like it cannot have a relative max, it cannot have a relative minimum. Okay? It can have a spot right here maybe. I'm looking at the second graph. You can have a spot here where the graph is flat, but it can only be for one point. Okay, so this might be like a hill to climb, right? And there's no resting points on it, where it's like, there's no going downhill. It's just all uphill. The whole journey is uphill. This graph is all downhill. You can have one little point that's a flat spot. So like you can have like, right here you can have a little flat spot right there where it's not climbing or falling. It's just kind of horizontal tangent right there. You can have one horizontal tangent right there, or you can actually draw graphs with multiple horizontal tangents like this. So at this point, the tangent line is horizontal. At this point, the tangent line is horizontal. At this point, the tangent line is horizontal. You can draw that, but you cannot let the graph ever drop. Okay? Because as soon as the graph drops downward at all, so let's say we change this piece to like coming down even just a hair, you just failed the horizontal line test. Watch. There's a horizontal line that touches twice there. See it? Can't have that. So one-to-one functions are very, very picky. They have to pass the horizontal and vertical line test. Okay? So that's one thing you need to know. So what's so special about these kinds of functions that are always climbing or always falling, except for some horizontal tangents? What's interesting about these ones is they have inverse functions. The other ones do not. Okay? All right, so let's write one more sentence and then we'll move on. Only a one-to-one function has an inverse that is a function. This is a very important fact. Only a one-to-one function has an inverse that is a function. Okay? Yes?
When sine's not a one-to-one function.
You're right.
And its inverse.
You're right. We got a problem with all of our trig graphs. None of them are one-to-one. Okay, so bear with me a couple more minutes. All right, so one of the questions you need to know, or one of the questions you need to be able to answer is just simply, is this one-to-one? So we'll do some examples of that. This is the last sentence in case you didn't get it. Only a one-to-one function has an inverse that's a function. Okay, I'm going to go and move forward. Okay, so let's just do some generic, is this one-to-one type stuff. Okay, so is f of x 1 to 1? It's a yes or no question, and then justify. Justify your answer. All right, so the first one, we'll call example 1a. F of x is the set of points negative 2, comma negative 8, comma negative 1, 0, 0, 1, 1, and 2, 8. Is this thing one-to-one? Well, it turns out it is, because if you plot these points, there are a total of 5 of them, you will see that none of them have the same y value, which means it passes the horizontal line test, and none of them have the same x value, so it will pass the vertical line test. Okay, so one way I can tell right away that this is one-to-one is there are no repeated x's. So this graph would pass the vertical line test, and there are no repeated y's, so this graph will pass the horizontal line test. Which I'll abbreviate HLT, not to be confused with hummus, lettuce, and tomato sandwich. Okay? I know, it's a little random. All right. So I'm not going to draw it yet. Maybe we'll draw it later in the period. But I'm sure if we draw this thing, it's not going to have any horizontal lines that touch 2 points or vertical lines that touch 2 points. Okay, so this is my justification. I'm going to say yes, and I'll just put there are no. Also, there are no. Okay, so I kind of made this into sentence form. All right, what about this one? F of x is shown, so you get a graph. Okay. This is the sine function, right? This is going to be an easy one. You've already got the graph there. Is it one-to-one? No. It's not one-to-one. You can see if you draw a horizontal line, this thing fails miserably. In fact, not only is there not at most one contact point, how many contact points do we have? Infinite amount. 2 per period forever in both directions. So that's way too many. Even 2 is too many, right? And this is way too many. So, no, y equals sine x does not pass the vertical line test. That's what I meant. Doesn't pass the horizontal line test. Right. Okay, what about this one? Y equals sine x x is between negative pi over 2 and positive pi over 2. Okay, so you still know what the graph looks like, right? It's the sine wave. But don't be too quick to say no, it's not one-to-one. Go and sketch it out. So we know it's a sine wave, but we're restricted to draw only between negative pi over 2 and positive pi over 2. The instructions are telling us to stick to this part of the picture. Okay? So the graph actually looks like this. It's right between the first trough on the left and the first peak on the right, the first crest. So what we have here is a little sliver of the sine wave, just a small piece. Now, is that piece one-to-one? Yes, it is. That piece is certainly one-to-one. You can draw horizontal lines all day long. They touch once at most. Okay, so this is, yes, y equals sine x is not one-to-one on its own, right? But if we restrict the domain, to negative pi over 2 is less than or equal to x is less than or equal to pi over 2, that piece of y equals sine x is one-to-one. By the way, this red thing has a name. It is called the principal sine function. And it's written y equals capital S, I-N, x. Capital S, I-N, x. So the lowercase one is the full graph, and the capital S is the little one-to-one piece surrounding the origin. Okay? You think I might test you on that?
Yes.
Absolutely. In fact, all of our trig graphs, we can choose a piece of them that is one-to-one. Okay? All right, how about this one?
Mr. Short,
Yes.
does it work the same for like cosine or like tangent? Like if you do the capital? Like
Yes, there's a capital cos called the principal cos, and there's one called the principal tan wave. Yep. Yes, yes, yes. Okay, how about this one? Which part are we on? Part C? Part D. How about y equals x squared? This is a quick no, because y equals x squared looks like this. You should know that by now. And that thing fails the horizontal line test right away. Okay, so this one's no, y equals x squared does not pass the horizontal line test. What about this one? Y equals x squared, x is greater than 0. This would be a yes, because we would only be interested in graphing this part, see? And that thing is one-to-one. Okay, so you would say yes, y equals x squared is not one-to-one. But if we restrict the domain, to x being greater than 0, the graph is one-to-one. function is 1 to 1. Okay, so the restricted function is 1 to 1. Okay, so I think this is a fairly new idea for many of you. Unless you're listening really closely last year, the teacher went over this idea then. But never in the years before that, I don't think. Okay, so what we see is that some graphs are not one-to-one, but if you do surgery on them, you can create one-to-one pieces of them. That is the most important part of chapter 6.1, I think it is to know that the surgery can be done, and we will perform that surgery on all 6 trig functions. Okay? All right. So let's go on. Next thing we need to talk about is how to find an inverse. Okay? So how to find an inverse function. Okay, so typically you want to verify that it is 1 to 1 first. Okay? If it isn't 1 to 1, then there's no business, you have no business finding the inverse. Okay? So check that the function is 1 to 1. If someone says, here, find the inverse of y equals x squared, you should say, hold on, it's not going to be a function. You're giving me something that's not 1 to 1. If I'm going to find the inverse, just know this, it's not going to be a function. Okay? So that's something you need to know. Check that it's 1 to 1. And then you're going to switch x and y. And you're going to isolate y, if possible. Okay, for example, let's say you're given find the inverse function. That's, by the way, f minus 1 of x. So let's say you're given f of x is equal to, and for this one I will do 3x plus 5. Okay, first you want to verify that it is 1 to 1. It is. It's definitely 1 to 1 because if you graph it, it looks something like this. It passes the HLT, it passes the VLT. It's certainly 1 to 1. Okay, so 1 to 1. Check. Yes, it is. That's a yes check. Okay, now let's try switching x and y. Well, where's my y? That's the left side, right? F of x means y. So you would just make this your x and make this your y. And try to isolate the y. So for this problem, you would subtract the 5, divide by 3, and it would look something like this. Y is equal to 1/3 x minus 5/3. This is your inverse function. If you don't mind writing this for me, that'd be nice. F inverse is 1/3 x minus 5/3. I just basically subtracted 5, and then I divided by 3. Okay, that one's not too bad. Let's try another one. How about f of x is equal to x to the 5th minus 2. Is that thing even 1 to 1? Let's check. So x to the 5th, remember, looks like this. What does minus 2 do to the graph? Shifts it which way? Down how much? 2. Okay, so this is the graph of y equals x to the 5th minus 2. Do you think it passes the horizontal line test? Yeah, it does. And it's a function. So we should do this problem. Is it 1 to 1? Yes. Okay, so let's try it. We have y equals x to the 5th minus 2, but we're switching this to make it the x. So you have that. And I think it's possible to isolate y. Let's add the 2 over and do a 5th root. So if we add the 2 over, we get x plus 2, and when we apply a 5th root, it looks like that. So my answer is f inverse of x equals the fifth root of x plus 2. So far there are no new skills. No new skills. All right. Now, if you're doing a problem and it's sufficiently challenging and you're not sure you did it right, you might need to check your answer. Okay? So let's do another example. Part C. Find f inverse of x, then verify that your answer is correct using composition. Using composition. Also verify on a graphing utility. That means graphing calculator. Okay, so here's f of x. And it's going to be x minus 1 over x plus 2. X minus 1 over x plus 2. Now, as a class, we have not graphed these yet. These are called rational functions, and that's really in chapter 3, so we'll come back to it and graph it soon. But we're not asked to graph it really except with the calculator, so we don't need to know the graph. You can be sure, though, that this is one-to-one. So we'll skip that step where you have to verify that it's one-to-one. Okay, try not to graph it on the graphing calculator yet. That's sort of our last step. Okay, so here's the tricky part. If we're going to be switching x and y around, things are going to get pretty messy. This is what it looks like when you put the y in for the f. And when you start to switch the x with the y, don't graph it yet. You'll spoil some surprises. Okay. Oops. When you switch x and y, you're going to have this. A little bit of a problem here. We've got two y's, they're both on the right side, and we're supposed to isolate. So how is that even possible? Well, let's cross multiply. Okay. So if you cross multiply, you're going to have x times y plus 2 equals y minus 1. And then you would distribute xy plus 2x equals y minus 1. This is on my test. I promise you. And then, if I'm supposed to isolate y, we might be wise to get all the y stuff on one side, right? So why don't we subtract the y over to the left, but the 2x, he doesn't have a y in it, so let's move him to the other side. So I separated the y terms on the left and the non-y terms on the right. And then I can factor out a y. And lastly, divide. Okay, this is my inverse function. You can tell that you can give me any x now, just give me any old x, and I'm going to only be able to give you one answer, right? So if you give me like x equals 5, I'll say negative 11 sixths, whatever. Yeah, no. If you plug a 5, it would be negative 11 fourths. One answer. A one answer output on the inverse means that the original function was one-to-one. Okay? All right, so we've got two functions. They look very similar, and supposedly they're inverses. I would like to verify that they really are inverses. I mean, did I really do that right? You know? Okay, so listen, this is not one of those things where the good students check their work and the bad students don't check their work. The instructions said you must check your work using composition. It's not optional. Same thing is true on my test. If you feel good about your answer, that's great. But I'm going to take off points if you don't check your work in this following way. Okay, so to use composition to check our work, how do you do that? Well, what you do is you find f of f inverse and f inverse of f to verify that they both yield x. just x. If f of f inverse and f inverse of f come out to just x, then we know our inverse is correct. This is supposed to say f, o, f. It's FOF, but it's one of them is inverse. Okay, so let's try it. First, let's find f of f inverse. So f of f inverse is going to have the structure of f, which is, where is that? X minus 1 over x plus 2. So it's going to have the structure of f, but it's going to have f inverse plugged in. So there's going to be a little minus 2x minus 1 here over x minus 1. And here, minus 2x minus 1 over x minus 1. That's f of f inverse. So how do you work with complex fractions? The easiest way to do it is just to multiply top and bottom by the denominators involved. So I see x minus 1s in my little denominators. So I'm going to multiply by x minus 1, top and bottom. This gives me negative 2x minus 1 minus x plus 1. And when I do this on the bottom, I get minus 2x minus 1 plus 2x minus 2, if you distribute properly. And this gives me, for a numerator, negative 3x, and on the denominator, negative 3. And all of this came out to simply x. That's a good sign. That means I most likely did everything correctly. Now we have to check the opposite composition. So let's do f inverse of f. It has the structure of f inverse minus negative 2 times something minus 1 all over something minus 1. But we have f's plugged in to this structure, so it looks like this. X minus 1 over x plus 2 and x minus 1 over x plus 2. This time I'm going to multiply top and bottom by x plus 2. And I get negative 2 times x minus 1 minus x minus 2. And on the bottom, x minus 1 minus x minus 2, which gives me, again, negative 3x on top and negative 3 on the bottom. It is x. I went kind of fast through the algebra there, so take your time with that. There's only one or two like that tonight. I think only one. But that is super important. This is proof that these are inverses. So here's the basic idea, right? Whatever f was doing to the number, f inverse undid it. For example, you plug in 10, right? First thing you do is you multiply by negative 2, then you take away 1, then you take away 1, and you divide. Well, f inverse is just going to undo all of that. F inverse's job is to take the number and then take away 1, and then take the number and add 2 and divide. Everything's exact opposite operations. So if you plug in 10, out pops 10 in the end. Whatever f was doing to the number to change it, f inverse is going to undo all of it. Okay, but this is the most secure and best proof that these are inverses. And this is what I need from you on the test. Okay, so make sure you study this example when you get a chance. Okay? Now we're supposed to verify with the graphing utility. So for that, I will use my graphing calculator. So I think I'll use WinPlot. Let me clear out this old function. Don't need that. Okay, so my function was, okay, so what was my f function? What was it? Was it x minus 1 over x plus 2, right? Yeah, that sounds right. We'll make that nice and thick. All right. Yeah, there's a one-to-one function for you. Okay, now let's graph the inverse answer. The inverse function was negative 2x, was it minus 1? Over what? X minus 1. And then for that one, let's make that a different color. Why don't we make that thing red for the inverse. with 3. You might say, oh, I don't know, is that correct? Well, if you graph the y equals x line, it should split this graph into 2 mirror images, and it really does. If you take this blue graph and you flip it over the black line, it becomes the red one, and vice versa. So you can see the good symmetry there. Pretty nifty. That's a visual confirmation. That's what they were talking about. Graph the function, graph the inverse, graph y equals x, look at it. Okay, I will warn you, when you guys graph on your graphing calculators, the plastic on this screen is wider than it is tall. Okay, so it's wider than it is tall. So when you get it graphed, it might not look quite right. It's a little distorted. What you want to do is do a zoom square. See option 5 there? And what that does is it makes all the x's and all the y's look the same size. So it'll actually look like my picture here. You'll notice on my grid here, this is a computer, so each of these boxes is exactly a perfect square. Your calculator can graph that way too, but you have to tell it to zoom square. Otherwise it'll look kind of twisted or kind of smushed. All right. There's one last skill you need. One last skill. The domain of an inverse versus the range of a function. Okay, because x and y are trading roles when you do an inverse, domain and range trade roles. Okay, so you need to know 2 very important sentences. Here they are, ready? The range of a function is the domain of its inverse. The range of a function is the domain of its inverse. And the range of an inverse is the domain of the original. Function. This is a really important idea. It's not a difficult idea. It's actually pretty simple. Let's look at an example of this real quick. A minute ago, we just did a problem where we got a function and we found its inverse. So in the previous problem, remember f was x minus 1 over x plus 2. I copied that right, correct? I'm going off memory. What if the problem said find the range? See, this is something we've never talked about. I've never once asked you to take a function and tell me the range, unless I taught you the graph for it. Right? I did ask you for the range and tangent and that sort of thing, but we drew a nice picture to look at. Right? What happens if you're given a function, but you've never learned how to graph that kind of problem? How in the world would you ever get the range? What you do is, your strategy would be, let's find the inverse, let's look at the domain, and then that'll be the range. It's like cheating. So here's my strategy. Okay? To find the range of f, I will find the domain. First I'll find f inverse of x, and I will find its domain, because the domain of f inverse is the range of f. And we're very good at finding domains. Like, we're excellent at that now. I mean, you should be pretty good at domain now. So we can turn a range question into a domain question. All right, so f equals x minus 1 over x plus 2. I could tell you the domain in like 2 seconds. What's the domain?
-2.
X is not negative 2, right? Set of all x's such that x is not negative 2. But what's the range? Well, let's look at the inverse, and we'll steal the domain from there, and that'll be our range. Okay? All right, so let's look at the inverse function. The inverse function was 2x minus 1 over x minus 1. Does that look right? I think so. Okay. This has domain. That was negative 2x minus 1 over x minus 1. Is that correct? Okay. It has domain, the set of all x's, such that x is not 1, right? This means that f equals x minus 1 over x plus 2 has range y's such that y is not 1. It feels like cheating a little bit. I don't feel like we really learned how to find range. I feel like we learned how to find domains, the domain of an inverse. But that is range. So what an awesome trick to find range now. Okay, so I'm going to just in 1 minute try to convince you that you know at least twice as much after today's lesson as you did walking in today. Okay? Let me try and convince you. You now can graph things like this. Why? You can graph this because you understand that this is just the inverse. Watch. You find the inverse. Switch x and y, right? This is going to be the inverse of a graph you already know. So watch. They're just going to take the 10 and add it over. Right? Cube both sides. Take away 5. You know how to graph that, don't you? Take a cubic and shift it to the left 10 and down 5. Okay, so if you can graph that, you can graph the one I have in black at the top. You'll just have to reflect it over the y equals x line. So you could just basically graph this, left 10, down 5, and it's a cubic. And then, here's your line of symmetry. Just reflect that sucker over the line. So it's going to basically be over here, right about here. There it is. So you know how to graph twice as many things as before now, because you know how to find an inverse. So for any graph that you don't recognize, try graphing the inverse. You might recognize that. And just flip it over the line. Okay? The other thing you now know is you now know how to find range instead of domain. That's twice as much knowledge. Right? For any function now, you can find the range without a graph. You just need to look at the domain of the inverse. So it's a pretty important lesson. All right, so your homework's on the board over there. It's just 17 problems. You have about 13 minutes to work.